Hello, my name is Albert Nardi. I work at AMPHOS 21, a certified COMSOL consulting company which offers services to markets such as nuclear and industrial waste management, mining, water resources and hydrogeology, geosciences and geochemistry, oil and gas, civil engineering. Today, I will show you an example of application related with a deep geological nuclear waste repository. Here, we can see an example of a high-level nuclear waste disposal system. This system is located deep underground. It consists of a tunnel gallery with thinner vertical tunnels. The waste is placed in the vertical tunnels. We assume symmetry in several directions and restrict our simulation to a piece of this system. A fractured zone with high permeability crosses the system at one end. It will be the source of groundwater inflow. The system is divided in 4 different domains. The canister, this is the part where the nuclear waste will be disposed. The buffer, this is the closest part to the waste. The purpose of this domain is to be an engineering barrier that isolates the waste and resists the high temperature generated. The backfill area, this represents the original access tunnel filled with material after its closure. And finally, the rock. Remember that the whole structure is surrounded by the rock, the geological barrier. The simulation will recreate the conditions of the system during 1,000 years after repository closure. During that time, several phenomena of interest will occur. There is release of heat from the waste. Groundwater will flow from the fracture towards the repository, saturating the whole system. And several chemical reactions will take place due to the disequilibrium between the inflowing and the resident pore water. So, in summary, the physics involved in this problem are variable saturated groundwater flow, conservation of energy, what can be seen also as transfer of temperature, and solute transport. And also chemical reactions. It is important to note that these 3 physics will be solved in COMSOL, but the chemistry part will be solved by the reactive called PhreeqC. PhreeqC is a chemical code widely known within the geochemical scientific community. The coupling between these 2 codes is done through a Java interface developed at AMPHOS 21, named COMSOL-PhreeqC. This figure tries to show how the information flows between the interface, the COMSOL server, and the IPhreeqc library. Note that the Java interface is the one who leads the program. It is in charge of calling both COMSOL and PhreeqC. COMSOL solves the physics, and it is fed with the aqueous water concentration resulting from PhreeqC calculations. Today, in this demo, we will follow the steps necessary to set up the problem with this interface. First of all, the implementation of a multiphysics problem with a conservative transport. Second step, the development of PhreeqC model. And finally, run COMSOL-PhreeqC. Let us start with the COMSOL Multiphysics model. We can see that we build the geometry using the COMSOL CAD tools. We have introduced a huge rock domain to keep the prescribed thermal condition reasonably far from the main release of heat from the canister. We have described different properties for each material. For the backfill, for the buffer, for the rock mass, and also for the water, which is present in the whole domain. We have included 3 physics. Let's start having a look to the heat transfer in porous media. It is implemented in the 3 domains. We have specified different parameters for each material. Note that some of these parameters depend on the water saturation degree. We have specified 2 fixed temperature boundary conditions. One at the top and the other one at the bottom. And also a heat source within the canister. With a given heat function, as we can see in the function prescribed, the heat decays over the time. Let's have a look now to the Richards equation. It only applies to the repository part. We have specified different parameters for each material. We have also two Richards equation model, one for each domain. This is due to their different saturation curves. Note that some of these parameters depend on the temperature, so it is also coupled with the thermal phenomenon. Regarding the boundary condition, we have imposed a flow over the fracture phase and also at the boundary edges. Finally, we set the solute transfer physics. Here, we first of all set a preliminary conservative transfer problem in order to be sure that the problem works and there are not, for example, stability problems. Later, this physics will be modified by the COMSOL-PhreeqC interface according to the characteristics of the chemical problem. It only applies to the repository part. And regarding to the boundary concentration, we have a concentration fixed at the fracture zone. Let's take a look to the meshing. We have built two meshes. A coarse one, suited for the thermal and flow problem, and another one for solving transfer equation. This is more refined. The reason for that is that hyperbolic nature of the transfer equation, which imposes more restriction to the element size. About the studies, we set two different transient steps. And step 1 for solving heat and flow, and which is solved over this coarse mesh, and another step 2 for solving the transport, which is solved over the transport mesh. These two steps are required for the use of the COMSOL-PhreeqC interface. So we are done. We can solve the study and take a look at the results. At this step, we show mainly three results. The temperature evolution at the canister. We can see how the canister heats the buffer and later it cools down, coming back to the natural temperature of the medium. Here cools down. The degree saturation of the media. As expected, the system gets saturated due to the incoming water through the fracture. And finally, the concentration evolution. Note that it follows the saturation front, but it's affected by diffusion also. Now, let's take a look at the necessary PhreeqC input files. First of all, observe that we need three water composition. One water in equilibrium with the buffer, another water in equilibrium with the backfill, and finally, the fracture water. Here, we can see the composition of one of these three waters, the fracture water. This water is brackish, and is quite rich in sulfide. To describe the geochemical reaction which may occur at each domain, we need two files. One file for the buffer domain and another one for the backfill area. Here we can see the reactions present on buffer domain. We find reactions in equilibrium, cation exchange, and surface complexation. Once we have these files ready, we can prepare the input file required by the COMSOL-PhreeqC interface. This is how the interface input file looks. The important part is to understand that the PhreeqC files are linked to the COMSOL model here. This is also the place where the different couplings are configured. In this case, for example, PhreeqC uses the temperature calculated by COMSOL. On the other hand, COMSOL uses an updated porosity, which takes into account the amount of mineral dissolution or precipitation calculated by PhreeqC. Now, we are ready to run the program. Let's see how the results look. First of all, we take a look at the chloride concentration. Units are in mole per kilogram of water. In this problem, chloride is a conservative tracer. This means that it doesn't react with the media. As can be shown in the animation, it has a similar behavior than the conservative tracer problem simulated previously. Now let's take a look to the exchanger. Here we will find the cation exchange phenomenon. On the left there is the calcium exchanger, and on the right the sodium one. Units are in percentage of exchange sites. We see how the exchanger is calcifying at the expense of sodium. In this case, magnesium and potassium play a minor role. Now let's move to the anhydride. The anhydride dissolution is the main factor that controls the geochemistry of the system, releasing calcium and sulfides into the solution, and thus promoting the pH buffering in the buffer and backfill due to calcite precipitation or dissolution. Here, units are in mole per kilogram of water again. From the beginning of the thermal period, anhydride gradually precipitates in the buffer due to the increase in temperature. Close to the fractured water, anhydride rapidly dissolves because groundwater is undersaturated with respect to anhydride. Now finally, let's take a look to carbonates. Here, on the left, there is the calcite, and on the right, the dolomite. Units are in mole per kilogram of water. A continuous transformation of calcite to dolomite is observed in the entire backfill, especially in the vicinity of the backfill buffer and backfill fracture interfaces. This is due to changes in the stability of the carbonate phases due to modifications of the pore water composition, promoted by the increase of brackish sulfide groundwater after 1000 years. And we hope you enjoyed the demo.